Hey everyone, welcome back to another video. Today we are going to be going through procedural island generation. This is similar to my 4-part series on creating terrain, however this is more focusing on islands. We are going to be starting from start. This is not a 5th episode, however you can see it that way if you want. In my scene I just have a few objects. I have a camera rig, a directional light, a water plane, and then a empty object which we're going to put the chunk manager on. So let's get right into it. Let's go into our scripts folder and create a C# script called chunk manager. So similar to the other terrain generation tutorials, we will be creating different chunks. And then each chunk's going to be generating its own terrain. However, in this script, we're not using two different scripts. So in the other one, we used a chunk manager and a terrain manager, or a terrain generation, whereas now it is two classes, but not two script objects. So let's make a public static instance of the chunk manager. So we're going to write public static chunk manager, and we'll just call it instance. And the reason why we're doing this is so then in Awake we can set it, and then from other scripts we can call it without having to have a reference to it. Well, the reference will be the static instance. So we can just set instance is equal to this. Cool. Underneath, let's also make a class called terrain generator, and then let's make a void called init, and let's actually make it public. And also, we'll be creating a void, public void called generate. Awesome. Okay. Inside of the start method, we will be generating our chunks. So we can generate our chunks within here. I'm kind of skipping over this because if you want the in-depth of all of what I'm doing here, you can go watch the other series. It's not using this exact system, but it's something very similar. Void generate chunks. And because we're going to be generating chunks in an X and Y plane, we need to have a public vector2 for the world size. And let's also make a public integer for the resolution of the chunks. Default the resolution to 16. Inside the generate chunks, let's create two for loops and set the values to be X and Y. This is going to be looping over the world size on the X and Y, and this is what's going to be creating the grid of terrain chunks. So inside we can create a game object. I'm just going to call it current, and let's set it equal to a new game object. And here we can make the new game object. So let's give it a name. Let's give it terrain, and then we'll just plus x multiplied by y. And what that will do is it's just going to give each terrain an identifier. There we can input some different components. So we need type of, and we'll need a mesh filter, we'll need a mesh renderer, and last but not least, type of, and here, mesh collider. And then we can also set the position. So current.transform.position is equal to, and just in case, we're actually also going to set the local position, because we can set current dot transform dot parent is equal to transform. Just put all the chunks under one object. Let's also set the local position to a new vector3 because we're working in 3D space. We're going to input x on the x multiplied. I'm just going to do a chunk size of 128. 0 on the y because we want it to be at 0 y level, and y multiplied by 128. Cool, so that should create a grid of terrain chunks, and what we can do is then on each one, whenever we create it, we can call the init and generate. So inside terrain generator, we're going to need a mesh filter called filter, and a mesh renderer, and a mesh collider. And in it, we're actually going to take a game object input and just call this the current. So then how do we get a reference to the terrain generator? Well, we have to create a new terrain generator. So Let's create a terrain generator, and we'll go a terrain generator. Just call it TG is equal to a new terrain generator. Then down here, after we create the object, we can go tg.init, and then we can input the current object, and then we can then call tg.generate. Awesome. So inside init, what is it going to do? Well, it's going to get the mesh filter, mesh renderer, mesh collider, and just assign it from the game object inputted, and it's just going to assign it to the mesh filter, mesh renderer, mesh collider variables that are in the terrain generator class. So let's go ahead and add that. So we can go filter is equal to the car.get component, and here we can get the mesh filter component, and just repeat these for the renderer and collider. So now that we get that, we can start getting into the generating. And what the generate's going to do is it's going to create the grid of vertices, then offset them, right? So mesh needs 3 basic things. It needs the vertices, the triangles, and then the UV data. We need a vector3 list for the verts. We need a int list for the tries, and then we'll also need a vector2 list for the UVs. Right, so at the start of generate, we can make the vertice list, or the list, or the array, a certain length, right? So we can go verts, we can set it equal to a new vector3 array, and in the array size, we can simply put our chunk manager dot instance dot resolution multiplied by itself. We also need to add 1 onto each side, as we're going to be creating a border. We can also set the UVs is actually just equal to the verts dot length, because they have to be the same size. Also, I forgot to add a mesh up here. So we're just going to create a mesh and call it mesh, and we're going to set mesh is equal to a new mesh, and this is the mesh class, which is going to have all the data on it, like the vertices and all that. Awesome. So now we can get into actually creating some vertexes. So let's create a new for loop for the x, and set it less than the resolution, less than or equal to the resolution amount. And now what is resolution? Well, we're going to create an integer called resolution, and let's set it equal to chunk manager dot instance dot resolution. Now what's interesting about this now is we can actually, instead of creating this long line, we can just simply go resolution plus 1. Now that we have resolution, we can then create another for loop inside for loop, and y, actually that's z, if we're going by proper world space, less than or equal to resolution. And this is where we're going to be creating the grid of vertices. We need a float for the y as well, so then we actually have x, y, z here. Let's just set that equal to 0 for now. And let's set the verts of, now just to make it easier, instead of going x multiplied by y, we can just go int I is equal to 0. You can actually put a comma here. And do int I is equal to 0 and x is equal to 0. And then at the end, we just need to remember the I++. So then instead, we go I is equal to a new vector3. We'll just go x, y, and z. And for now, that should be good for the vertices. Now, a little bit of math that we have to do. We actually have to multiply this by 128 divided by the resolution. Now, before I said that it is 128 is the size of each chunk. 128, that's 128 meters by 128 meters. I just choose 128 because it's a nice number. But what this is doing here is it's figuring out the upscale factor for each vertice. So this is when the resolution comes into play, right? So if we have a resolution of 64, there is going to be 1 vertex per 2 meters. Because 128 divided by 64 is 2. So it multiplies the x value by 2. And if you consider 1 iteration of x being 1 meter, which it is in this case, then it will upscale it. So if you only have 16, what's that? 68, it's 8. So it would 1 vertex per 8 meters. So it's a lot less detailed. Now you don't do that for y, but you also do that for z. So let's also just 128 multiplied by the resolution. And then we loop through the UVs, which is very easy. All we simply have to do is loop through the UVs and set them similar to the vertices. But we do want them in world space, so we do have to actually add world position. So at the top of generator, we're actually also going to calculate our position in the world space. But world pos is equal to filter.gameObject.position and .transform.position, my bad. And it's as easy as that. You know, I'll just convert this to a vector 3 so we don't have to go through the process. So now let's go UVs of I is equal to a new vector 2. And here we input the verts of I dot x plus world pos dot x. And then the verts of z, because we do not want the y value because that's going up and down. Verts of I dot z, my bad, plus world pos dot z. Well, yeah, world pos is z. Awesome. And that should be UVs finished. UVs dot length as well. Now onto the part which always screws me over, and it's the most annoying part for me and a lot of people. That's why I have a helper script open. The triangles. So let's set the tries is equal to a new int list, and it's resolution multiplied by resolution multiplied by 6, and that's just the way that the triangles are calculated. We're also gonna make an int for the tries, and because of that, we're gonna rename this to triangles instead. Triangles, set that equal to 0 for now, and int vert, set that equal to 0. Is pretty much the exact same as verts, but just for the triangles. Awesome. Let's create a for loop, and we're going to loop through the x and y again. And we're going to be looping through with the amount of the resolution, and in each one of these, we're going to be doing 6 integer calculations. Awesome. So I'm actually going to copy and paste this, because we've done all this before, guys. It's painful. Yeah, vert plus plus, and tries plus equals to 6. I know it's a bit of a cop-out, but I really can't be bothered going back and forwards. So that should be, and we clear the mesh just to make sure there's nothing in there. We set mesh.vertices is equal to vertices. I think it's actually verts. We set mesh.triangles is equal to triangles. We set mesh.uvs is equal to uvs, and then we go mesh.recalculate bounds, and we go mesh.recalculate normals, and then we go filter.mesh is equal to mesh, and we do not have a material to put on yet. So actually, let's go ahead and give a material input for the generate, and let's set it equal to mat, and let's create up here a public material for the terrain. And under here, we just enter terrain map. My bad, it's not UVs, it's just UV. And we also have to set the collider mesh, so let's go collider.shared mesh is equal to mesh. And then we also go render dot material is equal to mat. We also need to go a new vector 2 here. I don't know. New vector to array and then put vertical length. I don't know why I did that. And then I've also got res somewhere. Where did I put res? Anyway, chunk manager. Let's add the chunk manager script we just created to our chunk manager. Create a world size. Create a material. I already have a material set up. It's called ground. And let's click play and see what happens. Oh, look at this. We have a flat plane that we can now add some height to with our y value. So let's do that, shall we? Let's create the y level, the float y. Now, I'm going to introduce something kind of scary. It's called the sine function. Have you heard of it? So what we need for that is we actually need the distance that we currently are from the center. So let's work out where the center of the island is by simply getting that from the chunk manager. So we can actually really easily generate that. So let's create a public vector 3 and let's call this the world center. You know what, we can actually just create make it vector 2, make it easier on the distance function we're going to be using. So inside of the start method, before we generate the chunks, we're going to set world center is equal to a new vector 2 And we're going to be doing the world size divided by 2 multiplied by 128. And that's for the x. And then we'll be doing the exact same. That's actually world size dot x. World size dot y divided by 2 multiplied by 128. Cool. And then inside of the generate, when we get this, we can actually make a vector 2, call the world center, and we'll set it equal to chunk manager dot instance dot world center. So now let's just create a distance. So let's create a float, and we're going to call it distance. Set it equal to the vector 2 dot distance between. So we have the world position and we have the world center. So let's actually convert this into a vector 2. I knew that was going to come bite me because we couldn't use it in the function. Okay, dot x. And then we put this on the y to create a dot y for the vector 2. So basically we're getting the distance, and for now I'm just going to offset it based on the distance. So let's get the distance between the world center and the world pos. So we're going to get the distance. Float y is equal to distance. So theoretically, the further out from the center, the taller it will be. World pos dot y. Because I changed world pos. Awesome. We are getting the world pos, and we're not adding our own current position on. So let's just create a vector 3. Or vector 2, sorry, and let's call this the vertex world pos. Set it equal to a new vector 2, and let's figure this out. So we can go world pos dot x, world pos dot z, add x and add z, and instead of world pos we put in the vertex world pos. Oh, and my bad, we actually need to use the z for that. We actually are going to use the local position up here. And then also when we're adding x, we need to actually make sure that we're multiplying by 128 divided by the resolution. So I'm just going to yoink that code, bring it over here, that to z, save, go back to Unity. And now we have this really weird looking cone, but it's helpful. Because now that we know the distance, we can actually use the sine function. So let's slap that in. So let's use mathf.sine and then do the distance, and it will be bumpy. It will be very bumpy, and it will have these really cool ripples in them. Now this is what the sine function basically does. We also need to multiply by, we're just going to multiply by 150 just to give us a really nice value. Let's also divide this by 10 so we can get some really stretched out noise. There we go. So, as you can see, we're getting, you know, very stretched out, thinned out noise, but this is basically what sine waves are. It goes up and down, up and down, up and down, and because we're doing it by the center, we are getting these rings of sine waves going around and around. Now, this is actually what we want, and what we can do inside here is actually add 90 to the value, because if you remember me saying, is actually that sine waves, the 90 is equal to 1, right? If I were to sine 90 right now, we would get something that's completely above the ocean. And that's just because they're all at 1. So let's introduce some more variables. Let's create a public float for the island radius. Let's just set that equal to 900, shall we? Cool, now let's figure out some cool math. We're going to want to clamp the value, and the reason for that is because we want to basically have one island. If we have multiple sine waves, I mean, we could just stretch it out really far, but it's not actually going to be only one island. It's always going to have, if you make the world big enough, it will be multiple islands, which we don't want, and they'll all be uniform in shape and size. So what we want to do is we want to clamp the value, so then we only have one island in the center. So that means we clamp the value, meaning that it goes from 0, which is 0 when you input it into sine, to 90, which is 1 in sine, and then 180, which is 0 in sine, and then it flattens out through the whole rest of it, so we're not going to get any other islands apart from the one shape in the middle. So let's clamp, and we're going 1 plus the distance. Now, the reason why I'm doing 1 plus distance is because we're going to be dividing, and we do not want to divide by 0. Divided by resolution, divided by the island radius. So we can go chunk manager, dot instance, dot island radius. Now we could probably turn this into a value, which we probably want. So let's go float island radius is equal to chunk manager, dot instance, dot island radius. So we can just go island radius here, divided by island radius, and we want to clamp this between the values. So what is that end there? We're going to clamp this between 0 and 1 instead. And then we are also going to be adding 90 on in the center here, so we get the initial bulge. Let's also remove that multiply by 150. So let's now set y is equal to that. Yeah, and actually, yeah, we'll keep it 150. We're supposed to add 90 on at the end. My bad. After the clamp, plus 90. It's gonna load the map, and you know what? We can actually create some improvements to our code, so then yeah, we can figure this out better. Anyway, and as you can see, we have this very nice looking mound in the middle of our screen, and let's actually fix this. So let's turn the generate chunks into an IE numerator, and so we can create them one after another. So let's start the coroutine of generate chunks. And then after each one of these, we can simply just yield return null. Actually, we're just going to do 1 per frame. And because of this, we actually need to be using the system.collections and system.collections.generic. Let's actually wait for seconds. Cool. Let's also just decrease the island radius to something like 100. There we go. And as you can see, it's going to be generating. It's going to create this sad little mound. Maybe increase it to 300. It's just about experimenting, really. And as you can see, it's going to create this little mound. And yeah, this is the basic concept of creating an island. It's pretty simple. And what we're going to do now is we're going to add a little bit of noise to it. So the way I like to add noise, and the way I think you should, is using Perlin noise instead of creating your own. You can create your own. It's just hard. Anyway, the way we do this is we multiply by a value. So let's remove 150, and let's multiply it by mathf.perlin noise. What Perlin noise is it's a noise function which takes in a coordinate and outputs a value between 0 and 1. So let's get the vertex world pos.x and the vertex world pos.y, and we can scale this out a bit. So 0.01 probably is a good amount. Multiply by 0.01. Now, I'm not going to add a seed into this, but if you watch my other series, you can figure out seeds pretty easily. It's, you know, it's whatever. Let's also make the float called the island multiplier. We're going to be multiplying it by either 0 to 1. So let's actually say float y is equal to the island multiplier multiplied by 150, and this is just the scale. Now if I click play, we're going to get a lot of noise, and it's going to look pretty cool. We're going to get these little cool looking island little things. Now if you want to, you can actually multiply the Perlin noise by the sine, but I actually really like the way that these little islands turn out. You probably want to make the noise a bit more spread out, so you get some bigger islands. However, if you like the islands, you can also make the value random, so you get, like based on Perlin noise, so you get random islands in the middle of nowhere. Kind of cool. So there we go. If we generate it now, we get these island looking shapes, and it's pretty cool. Now we are going to be adding to this island multiplier a little bit of noise, a little bit of everything. So let's island multiplier plus equals, and here we can just go nuts with the noise. Let's just create Perlin noise all over the show. Now what we're actually going to do is move the sine into a new float. So let's call it float, and we're just going to call it sine, and we're going to set it equal to what we've calculated here with our sine. And then we can just set other multipliers equal to sine multiplied by the island, well, the Perlin noise, and we can just keep adding onto it. So we've got the sine, and what this means is we can actually multiply this by the sine value, so things get a bit more spread out the further out you go. So we just go multiply by sine. Some of them you don't, like this one, I'm probably not going to multiply by sine. What that means is, like, closer to the shoreline, you will get more, you'll get less extremes, which is what we had before. Cool. Now let's go into Unity. Yeah, see, like, I've probably ruined it a bit with the amount of noise, but hey, it looks pretty cool. Spread that out a bit, and yeah, so this is, you know, it's not perfect, but it's what I set out to accomplish when I made this little series. This is kind of a nice round off from the series, kind of tying everything together. Let's generate a huge world now. You see, it is generating those, so we do actually need to multiply everything by sine. Yep. Okay. Let's set island radius to something like 1,000, and let's watch it generate. Now that it's pretty much done, you know, it looks good. I'm happy with it. Anyway, guys, if you liked today's video, please give it a subscribe. This is probably one of the last tutorials I'm probably going to do, to be honest. Kind of don't like doing tutorials anymore. I want to focus more on devlog videos. Game I'm working on, which will have a devlog coming out soon. Anyway, guys, if you liked today's video, don't forget to subscribe. Also, these files will be on Patreon if you want to get them. I think it's like $5 a month or $7 a month. So go and give me some support. You get a bunch. You get this plus a bunch of other old projects which I've been working on, and you get them all for free. Well, not for free, but for, you know, the amount you pay. Anyway, guys, have a great day, and I'll see you guys next time.